Hi, I'm Ronen Shaltiel, and I'm going to talk about Yau's XOR lemma, and specifically, is it possible to improve Yau's XOR lemma using reduction that exploits the efficiency of an oracle? Yau's XOR lemma is a hardness amplification technique which converts mildly hard functions into very hard functions. So what do I mean by that? You give me a mildly hard function, namely a function f, such that for every circuit C in some circuit class, so let's think P/poly, the probability that C computes f correctly on a random input is smaller than 1 minus 1/3. And I'm going to call such a function a 1 minus 1/3 hard function. What the Yau's XOR lemma says is that if I consider the function f XOR t, which receives t independent inputs, applies f on each one of these inputs and XORs the output. So if I consider this function for sufficiently large t, then this function becomes very hard. Specifically, for every circuit C prime in the circuit class, the probability that C prime computes the function f XOR t correctly is smaller than half plus epsilon, where I was able to convert a function which is 1 minus 1/3 hard into a function which is half plus epsilon hard. And the precise statement says, for example, for the class P/poly, that for every function f, if this assumption on the left holds, then if I take t to be slightly larger than logarithmic, then the statement on the right holds, where I get epsilon, which is smaller than 1 over n to the c for every constant c. So I was able to convert a function which is 1 minus 1/3 hard into a function which is half plus epsilon hard, and epsilon is smaller than 1 over n to the c for every constant c. And this is great. It has many proofs and is very useful because we like functions which are half plus epsilon hard for small epsilon. So this is used all over in crypto and de-randomization. But there are things about Yau's XOR lemma that we don't know. So here are two specific open problems. The first one is, let's continue to consider the class P/poly. As I said, you can get epsilon, which is smaller than 1 over n to the c for every constant c. But can you go below that? Can you get epsilon, which is smaller than 1 over n to the omega of 1 sub-polynomial? We don't know the answer to that. A second open problem, now let's consider the class AC0 with parity gates, namely the class of constant depth circuits, which are allowed to use the gates and or not and parity. And here I'm asking, can you even get epsilon to be 1 over n? So we don't know the answer to both these questions. And in fact, both are open not only for the choice of t, which is slightly larger than logarithmic, but even if we allow t to be an arbitrarily large polynomial, we still don't know how to achieve these two things. So why do we care about these two problems? So let's start with the first problem. When you use Yau's XOR lemma to construct cryptographic primitives or pseudo-random generators, then the security that you get is epsilon. And we want to get as small as possible epsilon because we want to get better security. And current proofs do not give epsilon, which is smaller than 1 over n to the omega of 1. So that's one motivation. Another motivation for getting small epsilon is that we can look at Yau's XOR lemma as an imitation of the following information theoretic phenomenon. If you give me t independent coins, y1 up to yt, each with bias 1/3, then if I XOR all these coins together, I get a coin with bias half plus epsilon if I take t to be order of log 1 over epsilon. So information theoretically, I get half plus epsilon even for very, very small epsilon. I can get epsilon to be exponentially small even when t is polynomial, and we don't know whether this holds in the computational realm. Now let's consider the second open problem. So why are we interested in weak circuit classes? So let's take a look at the world of weak circuit classes. So here I drew a map of the world of weak circuit classes. On the left, we have AC0, the class of constant depth circuits with and or and not gates. Then AC0 with parity, Here we also allow parity gates. Then TC0, here we also allow majority gates. And then we have classes with larger depth like NC, NP/poly. And let's consider the majority function. Functions on the right, functions here, can compute the majority function by definition, whereas functions on the left, like AC0 and AC0 with parity gates, are known not to compute the majority function. And it turns out that the following thing happens. Once the class is sufficiently powerful to compute majority, then we can prove Yau's XOR lemma, so that's great. But then the natural proofs barrier of Razborov and Rudich kicks in, and it is hard to prove circuit lower bounds. On the other hand, if we consider these weaker classes that cannot compute majority, then for these weaker classes, we have lower bounds. They cannot compute majority, for example. But for these weaker classes, we don't know how to prove Yau's XOR lemma. So about 12 years ago, in a joint paper with Emanuele Viola, we called this the lose-lose principle, saying that you can only amplify the hardness that you don't have. And this is especially frustrating for the class AC0 with parity gates, where we do have mildly hard functions like majority by the lower bounds of Razborov, but we don't have very hard ones. And this is a reason why we don't get very good pseudo-random generators. Pseudo-random generators for AC0 with parity gates have pathetic stretch because we don't know how to get very hard functions so that we can afford the hybrid argument. So this is a barrier that prevents us from constructing pseudo-random generators with large stretch. So what do complexity theorists do when we can't prove something? Well, we make excuses. And in fact, there's a long line of work making excuses why we can't prove these two open problems, why we can't solve them. And obviously, when you talk about excuses, there's a hierarchy. So you can start with very weak excuses, like the dog ate my proof. But obviously, the kind of excuse that we want is that you can't solve these two open problems with all existing techniques. That's the gold standard, right, of excuses. So where are we? Somewhere in the middle between these two excuses is the following excuse. You cannot solve these two open problems with black box techniques. And it took some time, but today we know how to do that, right? So there were issues whether the proofs use adaptive or non-adaptive techniques or uniform and non-uniform techniques. But today, after this long line of work, in a recent work with Greenberg and Viola, we're able to prove that you can't solve these two open problems with adaptive non-uniform black box techniques. And this is the most general class of black box techniques that we can think of. So at the moment, in terms of excuses, we are here, right? This is the level of the excuse that we are achieving. You can't prove with black box techniques. The problem is that there are related results in the literature, not Yau's XOR lemma, but related results to hardness amplification that do use non-black box techniques. So this is starting from a joint paper with Gutfreund and Tashma from 2005, but perhaps the most famous example is a recent work by Hirahara, which gave a worst case to average case reduction for NP. And this reduction is non-black box. So the technique that is used by Gutfreund, Chartier, and Tashma, or by Hirahara, is something that I'll call a class reduction. These are proof that rely on the efficiency of the adversary, which is breaking F XOR T. And I'm going to explain this in the next slide. So now in the literature, we have techniques which are non-black box. These class reductions are non-black box. And we don't have excuses why we can't prove Yau's XOR lemma, why we can't solve these two open problems, because maybe we can solve them with non-black box techniques. Moreover, these new class reductions are known to break black box limitations in related setups, right? So there are examples in the literature where class reductions are able to break black box limitation. So this is the situation before this work. And what do we achieve in this work? So in this work, we improve the excuse. We show that you cannot solve these two open problems even if you use class reductions and even if you use strong class reductions, non-uniform class reductions. So we're able to improve the excuse from saying that we can't solve these open problems with black box techniques, even we can't solve these open problems even with class reductions, even with some non-black box techniques. And the important contribution in my mind is that we are able to give impossibility results even for non-black box techniques, not only for black box techniques, but it is possible to show impossibility results for non-black box techniques. And in the fine print, I should say, but in the paper, there is a discussion of whether our result rule out the most general class reduction model that we can think of. And it's arguable whether we rule out the most general version of class reductions. You can go to the paper if you want to have more details, right? But the important take-home message is we are able to prove impossibility results even for non-black box techniques. So now I need to tell you what are all these objects. What is a black box reduction? What is a non-uniform reduction? What is a class reduction? Let me give definitions of all these objects. So we are interested in proving Yau's XOR lemma. Namely, we need to show that for every function f, if f is 1 minus 1/3 hard, then f XOR t is half plus epsilon hard. This is the statement of Yau's XOR lemma. And we will be interested in proofs by reduction. So what is a proof by reduction? This is an oracle procedure, a reduction with an oracle, which performs the following task. For every oracle C prime, which breaks the security of f XOR t, namely for every C prime, such that the probability that a C prime computes f XOR t on a random input is larger than half plus epsilon, the reduction is supposed to implement a circuit C that breaks f. More precisely, if I give the function C prime as oracle to the reduction, this adversary C prime which broke f XOR t, and I consider the function C of x to be the reduction with oracle C prime on x, then I want this computation to break f. More precisely, it is required that when the reduction is given oracle to such a C prime, then the probability on a random input x that the reduction computes f correctly is larger than 1 minus 1/3. And you can see that such a reduction indeed proves Yau's XOR lemma. If you give me an adversary C prime which breaks f XOR t, then the constructed circuit C breaks the security of f. Okay, so now what do I mean when I say a black box reduction? When I say that a reduction is black box, I mean two things. The first thing is that the way that red interacts with its oracle is only using queries. More specifically, here is the reduction red, and here I wrote down the truth table of the oracle C prime. This is the exponentially long truth table. We imagine that this truth table is hidden inside a black box, and the only way that the reduction can access it is that it asks queries to some positions of C prime. Maybe it asks C prime in some position, and it receives an answer, and queries can be adaptive or non-adaptive, right? So red interacts with C prime only using queries. Another requirement that I make from black box reduction is that since this oracle C prime is hidden in a black box, then for every C prime, even an inefficient one, if C prime breaks f XOR t, then the reduction with oracle to C prime must break f. It has to perform. Now this is somewhat strange because I'm not interested in oracle C prime, which are inefficient, which are not small circuits. But in a black box reduction, I require that for every C prime, even an inefficient one, If C prime breaks Fx or T, then the reduction with Oracle to C prime breaks F. So this is a black box reduction. Now, let's take a look at non-black box reduction. What do I mean when I say a class reduction? What is a class reduction? So in a class reduction, I'm going to modify the second requirement. I'm no longer focusing on every C prime. I'm only making the requirement for every Oracle C prime, which comes from some class of efficient functions. Think P/poly or AC0 with parity gates, depending on the context. So I'm only requiring that the reduction performs if it receives access to an Oracle C prime, which comes from some efficient class of functions. And I should say that most limitations on black box reductions are proven by designing an inefficient Oracle C prime on which the reduction cannot perform. And this is no longer possible for class reductions. In class reductions, the reduction doesn't have to perform if it is given access to an Oracle which is inefficient. So now I have explained what is a class reduction. Now let me explain what is a non-uniform reduction. And non-uniform reductions can be non-uniform black box reductions, and then they can be non-uniform class reduction. So what is the issue of non-uniformity? So in a non-uniform reduction, I'm going to modify the first requirement in black box reductions. The first requirement was saying that the way that the reduction interacts with the Oracle C prime is only by queries. And in a non-uniform reduction, this is no longer true. The reduction is allowed to call a friend, this shady looking character in a raincoat, and this character can look inside the black box and can examine the entire truth table of the Oracle, the entire truth table of C prime, and send to the reduction an advice string, alpha, which is an arbitrary function of this truth table, C prime. And the only limitation on alpha is that alpha is short, right? So if the truth table is of exponential length, you can imagine that the advice string is of polynomial length. So the reduction interacts with C prime not using only queries, but it is first allowed to receive an advice string, alpha, on C prime, which is an arbitrary function of C prime. The only limitation is that it is short. And then it is also allowed to interact with C prime using queries. Now, I think that at first glance, this looks like a very strange form of a reduction. Why are we allowing the existence of this shady looking character? Why is the reduction allowed to do that? But it turns out that all known proofs of Yau's XOR lemma use non-uniform black box reduction. And this is for good reasons. They have to use this shady looking character. And if you're a coding theorist, when you're used to this phenomenon, essentially what happens is that the relationship between a non-uniform reduction and a uniform reduction is kind of like the distinction between list decoding and unique decoding. And this is explained more precisely in the paper. But for now, just believe me that we need to study these reductions. These are the kind of reductions that show up in the literature. Another comment that I want to make is that it is difficult to prove impossibility results for non-uniform reductions, even if they are black box. This is because that when a reduction is non-uniform, we can't assume that the reduction didn't receive any information on positions that it didn't query. This is because this shady looking character in a raincoat is able, even in a 1 bit of advice string, to send the XOR of all the positions in the truth table. So the reduction may get a little bit of information on every bit of the truth table, and we can't assume that the reduction doesn't have any information on unqueried positions, which is what we usually like to assume when we're proving black box lower bounds. So now that I've told you what is a non-uniform class reduction, I'm ready to tell you what our result is. So what is our result? Our result is that it is impossible to solve the 2 open problems that I showed you, open problems 1 and 2, on Yau's XOR lemma, even if you are allowed to use non-uniform class reductions. More formally, what we prove is that we prove a lower bounds on the number of queries that such a reduction makes, a non-uniform class reductions, and this translates into the impossibility results for open problem 1. And we also prove a lower bound on the circuit depth of such a reduction when viewed as an AC0 parity circuit. And this is what translates to the second, to the limitation of the second open problem. So our result is that it is impossible to solve open problems 1 and 2, even using these very strong non-uniform class reductions. So now let me conclude. So the main issue in this work is trying to understand the power of class reductions, which are non-black box. It is known, as I said earlier, that in some cases, class reductions are able to break black box impossibility results. But what we show in this work is that at least in the setting of the XOR lemma cannot be improved by class reductions, even if they are non-uniform. And for me, the significant thing in this work is that it is the first impossibility result on non-black box reductions, at least to the best of my knowledge, in this setup, right? In the setup of Yao's XOR lemma. So it demonstrates that we can show limitations on some non-black box reductions. Now let me move to some open problems. So in this paper, we rule out hardness amplifications, transformations of a form F to F XOR T. But we would like to extend these limitations to general transformation, no matter how you transform F to some harder function, supposedly harder function F prime. And this was achieved in earlier work, I told you, with Greenberg and Viola, in the case of black box reductions, for non-uniform black box reductions. So for non-uniform black box reductions, we can rule out general transformations. And here we can only rule out transformations of a form of Yao's XOR lemma, or slightly more powerful transformation. In the paper, we also show an extension to transformations which are achieved using explicit linear codes, but not for any general transformation. So an immediate open problem is to try and extend this work to a general transformation like it was done in the previous work. So that's an immediate open problem. But let me conclude with a more provocative open problem, courtesy of Emanuele Viola. So here's a question that Emanuele asked. Is the XOR lemma for AC0 with parity gates even true? Maybe the reason that we are having such a hard time proving it is not because it is hard to prove, but because it is in fact not true. And we may even have the tools to give a counterexample. So specifically, I'm asking the following question. Is it true that if you take t equals order of log n, or maybe you can extend it to t equals poly n, is it true that for every f, if f is 1 minus 1/3 hard for AC0 with parity gates, then f XOR t is half plus 1 over n hard for AC0 with parity gates? Maybe this isn't true, and somebody can give a counterexample. Okay, so that's it. Thank you very much for listening to the talk.